All right, let's move into our new unit fully. The last couple of days we've been reviewing Unit 4 on just basic linear regression information. So now we're going to move into actually finding out more information about lines. Because if, say, we want to find out the relationship, how are these two quantitative variables related? Okay, so here's an example. Do students who sit in the front rows do better than students who sit farther away? A teacher randomly assigned 30 students to seats at the beginning of the semester and then recorded their exam scores at the end of the semester. Would a negative slope provide convincing evidence that sitting closer in row 1 would cause a higher exam score? Or is it plausible that this association is purely by chance, just random, due to random assignment, random variability, sampling variability, sorry. Well, to test this hypothesis, we are going to run a hypothesis test for that relationship between those two quantities. And what we're going to be testing for is a slope of that relationship. The slope of the relationship between two quantitative variables to see if there actually is a linear relationship between x and y. Okay, so what would this look like? Well, we would have a parameter, and again, we're testing the slope. So we need a variable to represent slope. So the variable that we use to represent slope is beta. Now, think back, we used beta another time. When was that? Well, that was the probability of a type 2 error. Remember, alpha was the probability of type 1 error, beta probability of type 2 error. Not related, not connected. They're not the same thing here. Okay, so unfortunately, here's a separate variable that we're using to represent beta, the slope of the relationship between x and y, because we want to see if there really is a linear relationship between those two variables. So what would our hypothesis statement be? The null hypothesis, nothing's happening, no big deal, nothing's going on. There's nothing, no relationship, no linear relationship. Well, what would that do? That would set our slope equal to 0. So we start off saying nothing happening, null hypothesis, slope is 0, until you prove it to me or you have evidence that there is a slope greater than, less than, or not equal to 0. All right, now our assumptions in a hypothesis test are a little bit more involved than just random independent large enough. So we're going to have to get to that later. In fact, that's a separate lesson in itself. It's on day 4. Okay, so we'll come to that in a few days. And so we will name this the linear regression t-test for slope. Now let's recall why t-tests. So remember that t-tests are being used. So t-test because we only have the sample's standard deviation. Okay? Not population standard deviation. Population standard deviation. Okay, so same thing here. We don't have the population standard deviation for the slopes, so we use t-test because we only have the samples standard deviation. Okay, so now let's move on. So for this test statistic, there's a couple different ways that you can come up with this, and it actually depends on if what kind of information you have been given. Okay, so we wonder if you've been given actual data, or if you've been given a computer printout, or what's happening with that. Okay, so there's the issue. So we'll work through that. We'll discuss if you've been given individual data or a computer printout, how you handle that. Okay, so here we go. Degrees of freedom. Remember how our degrees of freedom for t-tests were n minus 1, because we had one variable and we had one degree of freedom because you could pick things until you had one left over. Well, there's more involved into the reason why that's n minus 1. But in this case, there are two variables. Think of it this way. A line is two-dimensional. It's not just one variable's worth of data. It's x's and y's, two dimensions. So therefore, our degrees of freedom is going to be n minus 2, because we need two leftover spaces to represent those two variables that are left. All right, and then from there on out, the test is the same as it has been. You decide, you compare your p-value to alpha, you decide if you reject or fail to reject, and then you see if you have evidence of a slope, a positive slope, negative slope, or not. Okay, so let's try one. Here we go. So we're going to take that same problem that I posed to you a minute ago. Do the students who sit in the front rows do better than the students who sit far away? Would this negative slope provide convincing evidence that sitting in a closer row causes a higher score? Okay. Now, a couple things. So here's the data. There are 6. So this is row number 1 because they are closest. These numbers, at first I struggled. I was like, are these categorical, the row numbers? Well, they're a quantity representing a distance. So they are a quantity amount. So they are considered quantitative. Okay, so we can go with that because that is a number line relationship. So here are the row numbers and the exam scores that are associated with those. So you can go start putting this into your lists, into your calculator. I don't think mine are in there right now. I had done something else, but you can go ahead and start putting those in your list while we're talking about this. So was this an observational study, or was this an experiment? What did we have? Well, if you remember, on the previous page, it described that the teacher, actually it says it here also, the teacher randomly assigns 30 students 2 seats at the beginning of the semester. So this random assignment means that it's an experiment. Experiment because the students were randomly assigned to a row. If the students got to pick their own, okay, then that might not play well. That could mean that the students who pick up close maybe naturally are more studious and want to be in on the action with the teacher, and as opposed to the ones in the back who want to be at the back of the room not paying attention, that kind of thing. Okay, no judgment here in class as to those where you chose your desk. Okay, so next question. Why is it important that the teacher, to do this experiment, there had been random assignment to seats rather than letting them choose? Well, I just kind of talked about that. So remember, we need to say we randomize to reduce bias. We randomize to reduce bias, reduce bias. So we random assignment to a row, that explanatory variable, reduces bias. And there's 2 things we want to say about that. Not only do you say that it reduces bias, it's happening because you are spreading the unknown traits, that should be unknown traits, evenly. When you need to spread unknown traits evenly, randomize, randomize. When you need to spread unknown traits evenly, randomize, randomize, randomize to reduce bias, reduce bias. Okay, so the idea is with this process of that random assignment is that then the only difference between the treatment groups is the treatment itself. Therefore, cause and effect can be concluded. Okay, so that's a big deal there. All right, how many variables were being measured here? Are they categorical or quantitative? Well, we kind of already talked about that. 2 quantitative variables. Again, I mentioned earlier why we're considering rho a quantity because it is a measurement of that distance. Now, it's discrete, not continuous. It could be continuous because have you seen the desks in my room? They're like all over the place, as far as not in straight rows. Okay, so we could measure distances and make it a little bit more continuous. But this was done in terms of rows and then the exam scores. What are the explanatory and the response? So the row number is our explanatory and the exam score is the response. Now, let's talk about something here because this is going to play into the rest of this unit. So here's a calculator thing. We have always done stat over to calc to get the equation of the line. Looky here, there's 2 options. You can either do linear regression. Since Algebra 1, you have been doing this linear regression number 4. Okay, stat over to calc right here, number 4, linear regression. So I want to point out to you, look at number 8. It also says linear regression. So study the differences between number 4 and number 8. Look at that for just a moment. So they will compute the same equation of the line, but what will be different? What will be different is the variable that they use to identify as slope and y-intercept. In the past, we've done y equals mx plus b, and so a was our slope and b was our y-intercept. Okay. Well, it is important that you know when we are doing this unit, a little b, and actually even on your formula chart for your statistics formula chart, a lowercase b is representative of sample slope. Capital beta is representative of the population's slope of all lines that can be made. Little b is a sample's slope. So I would like to pose to you, and I'm going to do this during this unit. I'm going to use StatCalc number 8, not number 4's, so that the B that appears is representing the slope, and the little a is the y-intercept. Okay, so whichever you use, keep that variability, those variables straight. Okay, and it will always tell you when you go and do the equation. Now mine is different data, so I'll go and do this real quick. So when I go StatCalc number 8, and then I have my data in L1 and L2, I may not even have anything in there. Mine's going to be different from yours because I was doing some other answer keys last night. See, looky here. It tells you up at the top, y equals a plus bx. So if you're ever not sure which variable is the slope, it's the one with the x. So in this case, b is the slope. Okay, and again, this was a problem for something else. Okay, so there's your little calculator warning. You may want to switch over to LinReg number 8. All right, so calculate the least squares regression line. So therefore I went StatCalc LinReg number 8. Look at what I have here. See, that's what I printed out. Predicted grade is negative 1.52 times the row number plus 85.95. Now I went ahead, and you have this as well. This is the plot of the data, row number against the grade. And then down here is the residual score against the row. So this is the residual plot right here. So what do you notice? Is there a pattern in the residual plot? No, there is not. So is a linear model appropriate? Yes, it is, because there is no pattern in the residual plot that I provided for you. Now, FYI, I did notice that whenever I ran, the correlation was a very weak negative, negative 0.21. So I wonder if that's going to play into the result that we have for our test. You know, in this case, I mean, if I was just kind of guessing, I was kind of predicting, what would you think? This is a pretty weak linear correlation. Do you think you're going to have evidence of a linear relationship? I don't know. I'm kind of doubting it. Maybe not. So we'll see. We'll see what happens if we have evidence of a linear relationship or not. Okay, state and interpret in context the slope. For every additional row that the student sits back away from the front of the room, the exam grade is predicted to decrease 1.52 points. And then our last one, state and interpret the y-intercept. Interpret the y-intercept. If the students sat in row 0, if the y is 0, the predicted exam score is 85.95. Okay? All right. Now let's go run the test. Here we go. This is it. Does this negative slope provide convincing evidence of that? Well, I don't know. What do I have to do to have statistical evidence? Run a hypothesis test so I can compare the p-value to alpha and make a decision. So here we go. All right. Here's our population parameter. Now, I wrote over here some little hints for you also. See, look, the little b is the slope of the sample. The beta is the slope of the population. So beta is the slope of the relationship between row number and exam score. Always are starting it with the word or the slope of the relationship, okay, between, and then identify x and y. Null hypothesis would be no slope right here. And then here, here's your options. Remember, HA, you've got these different options here. Well, they wondered about a negative slope. So therefore, I did beta for the alternative. Beta is less than 0 because we were wondering about negative slope. Alrighty then. Assumptions, not going to do it. Not going to do it until later. So that's nice. All right, so let's go. Oh, name the test. Linear regression t-test for slope. That's the name of what we're doing. A linear regression t-test for slope. And look, if you go stat over to tests, tab over to tests, and scroll up from the bottom, this is third from the bottom. LinReg t-test. We'll not ever do this 2-sample f-test, and we'll never do ANOVA. Other than that, you know everything in this menu. Crazy. Tomorrow we'll do LinReg t-intervals. Okay. So here we go. If you have the individual data points, you can just put them into your list in your calculator, which I had you do. Go run this LinReg t-test in the menu. So I did that. And here is the printout that we got. So the t-score, negative 1.14. The p-value, 0.1323. And degrees of freedom is 30 minus 2. There were 30 pieces of data, so 30 minus 2, degrees of freedom is 28. Okay? Now, FYI, this little s right here is the standard deviation of the residuals I might should have noted that. I tell you that also on your homework, your assignment. So the average amount that the actual score is varying from the predicted score is about 10.3 points. Okay, so what do we do now? Our p-value is greater than alpha. So what happens? We fail to reject. That coincides with what I kind of like was thinking. Remember on the previous page, we had a very weak negative linear relationship. Okay, now that is not the end all be all to determine if it's going to be that or not, if it's going to fail to reject or reject. Okay, it has to be done with the p-value. But this jives. This kind of makes sense to me that I'm going to fail to reject HO. So there is not evidence that there is a negative linear relationship between row number and exam score. Okay, so I'm going to stop this video right here because then the next one is going to talk about how to run a hypothesis test if you don't have the individual pieces of data. You just have a computer printout. This is a very common situation. So you need to understand what's going on with all of these things and look at all those arrows. There's crazy stuff happening everywhere. So I'll meet you back in the next video to discuss how to handle a linear regression t-test with a computer output.